Suppose I have to make a count mod 4 counter. Mod 4 counter means the sequence will start from 0, 1. Yeah, of course, because it is the up counter. So it will start from 0 and it will reach up to 3. So 0, 1, 2, 3, and then again it will come to the 0. So this is what we are interpreting. So the meaning of modulus, I already told you. Meaning of up counter, I already told you. Now let's talk about what is the meaning of this asynchronous or the ripple. I have already told you before. So if I have a mod 4 counter, so the total number of flip-flop that is needed is equal to, I know that m should be less than or something like the relation is something like that. Here n indicates the number of flip-flop. So n is equal to 2. So 2 number of flip-flops are needed. Okay. Now the question is, because I have a 2 flip-flop that is required for this counter designing. So both the flip-flop may also require some clock pulses. Okay. Both the flip-flop will require the clock input. So if both the clocks are controlled with the same signal, then we can call them the synchronous. But if both the clock pulses are not controlled with the same signal, then we can call them the asynchronous one. What does it mean? It means that, like I just calculated, I need a 2 flip-flops. Okay, having one clock pulse, some input and some output. And there is another flip-flop having some clock pulse, some input, some output. Okay, so if the output of first clock of flip-flop is connected to the clock of the second one, and so on, then this kind of arrangement we call them the asynchronous one, because the clocks are not controlled simultaneously. They are like the clock of the second flip-flop depends on the output of the first flip-flop, and so on. So this kind of counter we can call them the asynchronous one. If I'm talking about a synchronous one, then the synchronous means all the clocks are controlled with the single signal, and we can call them the signal. So here input will be provided, output is connected to the next input, and so on, something like that. So if the arrangement is like this, we can call them the synchronous counter. Okay, so this is the basic difference. Yeah, I will see all these things in more detail. Okay, so yeah, just if you can see here, if I have to make mod 4 counter, so I need 2 flip-flop, total states will be 0 to 3, and this will be the arrangement. Yeah, so let us try to make it properly. So it will start from 0 because it is the up counter. It will go to the 1, then it will go to the 2, next state will be 3, and the last state again it will come to the 0. So let us try to see few things, what will be the count and what will be the sequence that I have to follow. Okay, so let us see. Counters that will start from 0, it will go to the 1, it will go to 2, it will go to 3, and again it will be reset to 0. So this is the clock count sequence. Now let us talk about, suppose I have a 2 outputs of the flip-flops. So what should be the sequence? The first sequence will be 0, 0. Second sequence will be 0, 1. Third sequence should be 1, 0 because it is the up counter. And the last one is the 1, 1. And then again it should be reset to 0, 0. Okay. So what does it mean? If you see the sequences here, in the first sequence, there is no change in the A1. Okay. A1 should be as it is. But the A0 is changing from 0 to 1. So this is the first thing that is happening. Okay. 0 to 1. And then this 1 to 0 and 0 to 1 and 1 to 0. So the A0 is changing for all the times. Okay, so A0 is changing for each clock bit, means if I'm moving from 0 to 1, 1 to 2, 2 and 3, so every time A0 is changing, what does it mean? It means that it is indicating the least significant bit. Okay, so A0 is indicating least significant bit because at each clock the A0 is changing its state. Okay, and if the bit change after each interval, then we can call them, this is the LSB. Similarly, if you see here, for two times it was 0, 0, then 1, 1, then 0, 0. So we can call it, it is the MSB because I have only 2 bits only. So A1 is the MSB and A0 is the LSB. Okay, so this point may be clear to you. Now let us talk about what is happening with this one. So if you see here, A0, like if it is going from 0 to 1, then it is changing from A0, it's changing from 0 to 1. Yeah, so I think I can write here. A0 is changing from 0 to 1 and A1 is same. Okay, A1 is same. If we talk about this one, in this sequence, the A0 is changing from 1 to 0 and the A1 is also changing from 0 to 1. So A1 is changing from 0 to 1. Now if we talk about this one, here the A0 is changing from 0 to 1 and A1 is same, it is not changing, and so on. So you can say all these things, what is happening. Okay, so let me finish it. So A0 is changing from 1 to 0 and A1 is nothing but it is the same. It is changing from 1 to 0. So this is the sequence that it is going to follow. Now let us try to design the counter, how it looks like. Yeah, so this is the schematic of this asynchronous up counter. Up counter means like this input A0 that is connected to the next flip-flop A1, and here A1 is the MSB and A0 is the LSB. The output is connected to the clock pulse of this one. Okay, so this is really very important. Output is connected to the clock pulse of this one, the next flip-flop, and we can take the output from this one. And one thing that is important, like to make it toggle, I have to connect T inputs to the logic high, because we know that if T is equal to 1, then the output will toggle between each other. Okay, if T is equal to 0, so this is how we need to make this T is equal to 1. Okay, so this is the simplest circuit for mod 4 asynchronous up counter. Asynchronous is basically decided based on the clock, like what is how the clock is connected for the next flip-flop. Okay, and mod 4 indicates like, yes, because I have 2 flip-flops, so total possibility could be to about 2, means the mod 4 is possible. Mod 4 is possible, and because there is no other circuitry involved here and there, so we can call them, it is the mod 4 counter. And asynchronous, I have already told you. Up means because the A0 is controlling the A1, so we can call them the up counter. Okay, so if the Q0 is controlling the clock pulse, then we can call them the up counter, and if Q bar is controlling, then we can call them the down counter. Okay, so we'll see these things later on. Okay, so if we try to make, yeah, what the thing which I just told you is very important. Okay, what thing you have to consider, especially if you want to design a counter, the first thing that you have to consider, this T should be at logic high, so that you can make it the toggle state. Okay, second thing, if your objective is the asynchronous one, then the output of the first state should be connected to the clock of the second one. So this is the second thing that you need to consider. Okay, to make it asynchronous. And to make it synchronous, like output, like all the clocks will be connected to the same input. Third thing that you will observe just by seeing the pictures, like if the LSB is controlling the clock or the next stage, then we can call them the up counter, or the Q0 is controlling, then we can call them the up counter. And but if Q bar is controlling, then we can call them the down counter. Okay, so I will just tell you how to make it. Okay, so these are something that is needed. So the timing diagram will look like this one. So suppose I have a clock pulse that is changing from 0 to 1 and so on, and because if you see here, this is nothing but this is the negative edge trigger. This is nothing but this is the negative edge trigger. So the performance will be like this. Like the input should change at the negative edge side. Okay, so initially the output for both the flip-flop was 0. Okay, and flip-flop, like, because I have provided the clock pulse to this flip-flop 0, the first A0 will be reflected. Okay, so the A0 during this age, this A0 will change its state from 0 to 1. Okay, because it is going to toggle, because I have used a toggle flip-flop and initially it was 0, so it will change its state from 0 to 1. So the A0, that will become 1. Okay, and there is no change in the A1, because A1 that will be reflected once the clock, the next toggle will come. Okay, it will not be reflected at the same time. Okay, so this A0 will be maintained to 0. Now when the next toggle comes, then again, because this will be treated as a clock pulse for A0, so again, because the A0 was 1, so it will become 0. And now, because the previously the A0 was 0, A0 was 1, and during this one, because A0 is changing, so this A0 will act as a clock pulse for this flip-flop 1. So when this negative fall will come, A1 will change its state. Okay, so this negative fall will change its state from here to there. So that is why A1 will change its state from 0 to 1. So this is how they are changing. Now, one clear thing that you can observe from here, all this discussion, is that whatever the time period of this one is, let us assume the time period of the clock pulse was, let us assume it is the T. Okay, let us assume the time period of the clock pulse was T. So see here, the time period of the output of that flip-flop becomes 2T. Okay, that is why I already told you before, the flip-flop is nothing but, this is the frequency divider circuit. Okay, the frequency is divided by 2. Okay, if I'm passing any clock, any signal through any flip-flop, the output frequency will be divided by 2. Okay, so this is how we can observe. Similarly, if you see here, initially the output, if you talk about the time period for A1, so this will be nothing but it is the 4T. Okay, so after each state, the frequency will be divided. Okay, so these are some important things about the up counter. So if you have any doubt on this, you can ask the question, because if you know these things, rest other things we can move in the fast pace. Okay, so I'm just giving 1 minute time to think about this one. If you have any doubt at any point of time, please let me know. Then I can move ahead with the next circuit. Anyone? Okay, think about this. I'm just giving 1 minute. Okay, so if there is no question, then I can move ahead. Fine. Next one is some aspect that need to be considered in the asynchronous counter. Okay, what are those aspects that are very important? The first thing that we should consider is like the frequency division. Okay, I just told you, like, if I'm considering the FA0, yeah, because see, if in the previous slide we saw two things, A0 and A1. So FA1 was nothing but it was the actual frequency divided by 2. And if you see FA1, this one was FA0 divided by 2, or this was same as F divided by 4. So in general, if you want to say, suppose if I have n number of flip-flops, in that case, FAN, this is nothing but you can say like frequency divided by 2 to the power n. So this is the formula that you should consider, like how the frequencies are getting divided in after each state in the flip-flop. So output frequency is nothing but the input frequency divided by modulus, and this is the important thing that you should consider. Okay, where this n is the number of flip-flop, okay, and accordingly you can decide. The next parameter that we should consider is the propagation delay. What this propagation delay is and how it is important. Let us go back to the previous slide and then I will tell you what is happening here. Suppose if I have applied some clock pulse here, okay, if I have applied some clock pulse here, the flip-flop has some internal delay. Let us assume the internal delay is TD. So the A1 will be reflected after TD time period. Once this clock pulse changes its state, the flip-flop will take some time, and that time is the TD, which is the propagation delay of the first flip-flop, and the A0 will be reflected after, if the clock was executed at time 0, t is equal to 0, so at t is equal to TD time, this output will be reflected. Okay, now because this output, whatever the output I have, this is controlling the next state. So at each and the flip-flop delays again, let us assume it is TD. So the A1 will be received after 2 TD. Okay, 1 TD for this flip-flop and 1 TD for this flip-flop. So whatever the clock pulse I have, if I'm changing some clock pulse, it will take 2 TD time period to get it reflected at the output. So as we keep on increasing the number of flip-flop, this delay is going to be increased. Okay, and this is the problem of asynchronous kind of counter. Okay, so what is the problem? Let me repeat it again. The first, the problem is, yeah, so let me go back to the slide which I was telling you, and then we can discuss things. Okay, the propagation delay. So I just told you, suppose I have a clock pulse, I have just given the clock pulse, the A0 will be received at this time period. Okay, and so it will be changed after this time period, and it will be maintained for this period of time. Okay, again, what happens if the A1 is there? A1 initially is what, 0, so it will take 2 time TD time delay and something like that. So the important thing is, like, if I'm considering the TD time period for each flip-flop in the series, so the total delay, like, and we also know that what is the delay or what is the time period of this one. Okay, so it should be whatever the delay of the flip-flop we have, that should be within this limit only. Okay, so if I have increased the third stage, so the third state maybe it will start from here, the fourth state that will start from here, and might be it can cross this limit whatever I have. So it can also limit how many number of stages I can consider in the asynchronous one. Let me repeat it again what I'm saying. This is really very important. Let us assume I have A2. So A2 will again take 1 time TD. So here A2 will be received at 3 TD. Okay, 3 TPD. Suppose I have one more flip-flop, and then it will take again 1 time period. So A3, that will be received at 4 time TDP. TPD or TPD, whatever I'm saying. Okay, and if it is within the limit, that is fine. But the next flip-flop is not possible, because the next flip-flop timing is beyond this limit. This is not under this limit. Okay, and if it is beyond this limit, this stage is not possible. Like 5th flip-flop is not possible. So how we can increase the number of flip-flop? The first thing that we can do, like, we should try to reduce this TPD of each flip-flop. So this is one of the way, so that you can increase this one. Okay, so you can increase the number of the stages that you can involve. Okay, so this is the first point that you should consider. The second thing is, like, if you are not able to reduce this TPD, you can increase the time period, or you can reduce the frequency of the clock pulse. So if you are able to reduce the frequency, this time period will increase, and you can accommodate more number of flip-flops. Okay, so to overcome this propagation delay and increase the number of flip-flops, you can do 2 things. The first thing is, try to reduce the delay of individual flip-flops so that you can accommodate without changing the frequency of the clock, you can accommodate more number of stages. This is the first possibility. And the second possibility could be, if you are not able to change the propagation delay of that flip-flop, then you can increase the time period of the clock or reduce the frequency so that you can accommodate more number of stages. Okay, but still there is a problem. Like if you want to make your counter for high speed applications, in that case, the reducing the clock frequency is not a solution. Okay, so you cannot reduce the frequency for high speed applications. Okay, so this was the problem with the asynchronous kind of. Okay, so to overcome this problem, we need to go with the synchronous kind of counter. So what is a synchronous counter? I just told you, but I will discuss more things about this later on. Okay, hope the points are clear. If you have any doubt at this point, you can ask the questions. Otherwise, we can move ahead. Okay, so this is what the delay we can consider, and how many number of stages we can accommodate without any fault. That depends on the TPD and the time period. Okay, so this is important relation. So that the T clock pulse must be greater than or equal to n TPD, where n is the number of flip-flop that we can accommodate. So this condition should satisfy for the proper functioning of the counter. If it will not satisfy this condition, the counter will not function properly. Okay, so this was the problem. Okay, so hope the doubts, the points are clear, like how we are doing the frequency division and the propagation delay. So this is what you can do. Now, I just told you we can have a mod 3 counter as well. Mod 3 counter is also possible. And if you see clearly here, the mod 3 counter is nothing but, like, suppose if I want to make a counter with reduced number of stages, then modulus 3 or other counter is sufficient that we can make it. Okay, so let us try to see how we can make the modulus 3 counter. Here we are trying to make the up counter. Okay, so the counter that will start from 0, the next state will be 1, so it will go to the 0 to 1, and because it is the modulus 3, so the last stage will be 2, and then again it will come to 0. Okay, so 0 1 2 0 1 2 and so on. So this is how it will work. So let us try to understand the truth table of this one, how the truth table looks like, and then accordingly we can manage the things. Okay, so as I told you, I can have a counter clock pulse something like this. So the sequence will be from 0 1 2, and then it should come to 0 again. Okay, so this is the clock count. If we talk about A0 A1 which are the output of the two flip-flop, because see here the mod is 3, and if we check this condition, m is less than is equal to 2 to the power n, so the n is coming out to be 2. Okay, so we are getting n is equal to 2, and n equal to means the 2 number of flip-flop is needed. 2 number of flip-flop is needed. What it means? We can have a 2 outputs, which are A1 and the A0. Okay, now sequence will be 0 0 0 1 1 0, and then because for 2 bits I have a sequence like 0 0 0 1 1 0 and 1 1, but just after this one I want to come back to 0 again, so I just need to make it 0 and 0. So this is the truth table for the modulus 3 counter. Okay, so what will be the Boolean expression? The Boolean expression will be like, so if suppose if I want to make the third counter, like so this is what our requirement is, but instead of this, suppose if I am considering 3, so it will be 1 1. Okay, and this condition is not required. Okay, this condition is not required, and this is invalid, so the sequence should move from here to here, and this is not valid case. Okay, so how to make that one? How to make the circuit that can count like this, 0 to 1, then 2, then it should again move to the 0 without moving to the state 3. Okay, so let us first write what is the expression of this. The expression for like the first one is 0 1 0 is a1 bar a0 bar. Expression for second one is like a1 bar and a0. Third one is like a1 into a0 bar, and the fourth one is a1 and a0. Okay, so what I want, this is the desirable state, a1 bar a0 bar. A1 bar a0 is not desirable state. Sorry, this is also desirable state, and a1 a0 bar is the desirable state, but a1 a0 is the undesirable state. So when this comes, I need to clear all the values. What the clear role of the clear signal in the flip-flop? The role of clear signal is whatever the value in the flip-flop is, that must be clear immediately. Okay, so because this is not needed, so when this signal comes a1 a0 like 1 1, so both the flip-flop must be cleared immediately. Okay, so let us try to see how we can clear this thing. Okay, so because I just already told you I need 2 number of flip-flops, so here I have a 2 flip-flops, and because I'm considering it is the asynchronous one, the output of first flip-flop will be connected to the clock of this one, and so on. The clock pulse is given to the first flip-flop, and the input T0 and T1 are connected to the high. So this is the normal circuit, whatever we have already told. So if I'm not connecting anything, so this counter will start from 0, then it will go to 1, then it will 2, and then 3, and then it will come to again 0. Okay, so this circuit, whatever I can see, this will count from 0 to 1, then 2, then 3, then 0, and so on. But if I want to make something like the counter should stop or it should be reset to 0 after state 2, then how we can make that one? Let us try to see. I just told you reset signal will play a major role in this case. Okay, so see here, I just told you here a1 a0 is the a1 a0 is undesirable case. Okay, so if both are 1 1, okay, in that case the this should be reset, the flip-flop should be cleared, both the flip-flops should be cleared. So what we can do, we can simply we can end it, because a1 a bar is there. So if these both are 1 1, then it will generate 0. Okay, it will generate 0, and that will connect, and because if it is the clearing with 0, logic 0, then it will clear the logic. Okay, so this will connect to this one, and that will clear the ff1. So the a1 will become 0, and the same thing will be connected to the ff0, and because the same thing is connected, so output of both the flip-flop will become 0 0. Okay, so let me explain the working of this circuit, how it is working. If 0 and 0, a0 and a1 is 0 0, okay, if a1 and a0 is 0 0, in that case what I will get this output as 1, and if it is 1, this will not be clear, this will not be clear, so this counter will work. Okay, now so in the first clock pulse, this a1 will become 1. Okay, yeah, let me just simply show you the timing diagram, so you will be able to see here. So if a0 is there, so in the first clock pulse, a0 will be reflected from 0 to 1, and there will be no change in the a1. In the next clock pulse, what will happen? Once this clock pulse will come, then the a0 will change its state, and because a0 is changing its state from 1 to 0, a1 will change its state from 0 to 1. Okay, so 0 to 1 will come. In third clock pulse, this is 0, this is 1. Okay, and once the next clock pulse comes, see, this point is really very important, you should note this one. Once this next clock pulse will come, this a0 should change its state from 0 to 1, and this a0 will become 1. Okay, and if it is becoming 1, and because it will take some time, yeah, because this clock pulse we have executed, it will take some time, so immediately you cannot get the output that will be reflected, because this is nothing but this is a time td of the flip-flop a0. all the waveform that will be shifted by TD time period. So this TD time period that will give you, and because if it is high, then it will move to the 1. And at this time period, A1 will be shifted, A1 will be changed. And because in between, if you see this clock pulse, at this clock pulse, both A0 and A1 are high. So Y will become 0 for that period of time. Okay. And if Y is becoming 0, it will reset both the flip-flop, and again 0, 0 will come out. So this is how it is resetting the outputs, whatever we have. So, and so what does it mean? It means that the total time delay that required is NTPD plus TS. TS is the time period which is given over here. This TS is that important. So this TS time period, what is happening? Why I'm not able to remove it? So I'm not able to remove few things. Why it is so? Okay, so let us write here. So this is nothing but this is the TS. Okay, TS time period that decides how we can move ahead. Okay, so please think about this. If you have any doubt, you can ask the questions. Otherwise, I can. So this is how we can design the modulus 3 counter. Okay, so
can you explain that how is that spike coming in? Why?
Okay, let me, there is some error. I think there is some problem, so I need to check it out. 1 minute, right? Yeah. Okay, so can you repeat your question? What you said?
In timing diagram, how is that curve of Y?
Okay, this Y is nothing but this one. Okay, this Y is the output of this AND gate. Okay, so what will happen? If this is 0 and 0, so I will get high. 1 0, I will get high. 0 1, I will get high. But because this A0 is like changing its state from 0 to 1, and this change is only because of this TS. TS is nothing but the time period of this one. Okay, so TS, like, it will take some time to reflect it. TS is nothing but the delay of this one. Okay, so TS is nothing but delay of this AND gate that will take some time to take the decision. So even though the A0 was changed from 0 to 1, okay, it was changed from 0 to 1, and at the same time A1 was initially 0, then it was 1, and once this TS, after this TS time period, this Y will become 0, because initially the Y was 1. Okay, it will become 0 after TS time period, and once it will become 0, it will clear both the flip-flop, and if it will clear both the flip-flop, that will, like, both the outputs A0 and A1 will become 0 and 0. So this TS is nothing but this is a time taken by this AND gate to generate the output low, so that both the flip-flop can be cleared. So up to that time period, this output will be logic low, and then once this becomes logic low, because logic low, this will clear this one, and once both the flip-flops are clear, output will again becomes 1. Like this, Y will become again 1. So you will get some glitch over here, and this glitch is because of the delay of this AND gate. So this is nothing but this is the glitch. You got the point?
Yes, sir.
Okay.